Welcome to the series of e-learning modules on definition of probability, classical and relative frequency approach to probability. In this module, we are going to cover the basic concept of probability, definitions of classical and relative frequency approach, limitations of each definition of probability. By the end of this session, you will be able to know the basic concept of probability, classical approach and its limitations, relative frequency approach and its limitations, comparison between the above two. The word probability or chance is very commonly used in day-to-day conversation, and generally people have a vague idea about its meaning. For example, we come across statements like, "It may rain tomorrow," "The chances of teams A and B winning a certain match are equal," etc. All these terms, mostly, probably, presumably, likely, etc., convey the same meaning. That is, the event is not certain to take place, or in other words, there is an uncertainty about happening of the events in question. In statistics, we try to present conditions under which we can make sensible numerical statements about uncertainty. Business decisions are often based on an analysis of uncertainties such as the following. What are the chances that sales will decrease if we increase the prices? What is the likelihood that a new assembly method will increase productivity? Definition of probability. Probability is a numerical measure of the likelihood that an event will occur. Thus, probability could be used to measure the degree of uncertainty associated with the events listed above. The probability of a given event is an expression of likelihood or chance of occurrence of an event. There is no general agreement about its interpretation. However, broadly speaking, there are different schools of thought on the concept of probability. Probability values are always assigned on a scale between 0 and 1. A probability near 0 indicates that an event is unlikely to occur. A probability near 1 indicates that an event is almost sure to occur. Other probabilities between 0 and 1 represent varying degrees of likelihood that an event will occur. Hence, probability is nothing but a numerical measure associated with the occurrence or non-occurrence of an event. Probability is important in decision-making because it provides the way to measure, express, and analyze the uncertainties associated with future events. Assigning probabilities to experimental outcomes. With an understanding of an experiment and a sample space, let us now see how probabilities for the outcomes can be determined. In assigning probabilities to experimental outcomes, two basic requirements of probability must be satisfied. The first requirement is the probability values assigned to each experimental outcome must be between 0 and 1. If we let EI denote the ith experimental outcome and P of EI indicate the probability of this experimental outcome, we must have 0 less than or equal to P of EI less than or equal to 1 for all I. Call this as 1. The second requirement is the sum of all the experimental outcomes of probabilities must be 1. For example, if a sample space As k experimental outcomes, we must have P of EI plus P of E2 plus P of E3 till P of EK is equal to 1. Call this as 2. Any method of assigning probability values to the experimental outcomes that satisfies these two requirements and results in reasonable numerical measures of the likelihood of outcomes is acceptable. In practice, the classical approach, the relative frequency approach, and axiomatic approach are often used. Let us just recollect some of the basic concepts of probability which are required for the classical and relative frequency approach of the probability. A. Exhaustive cases. The total number of possible outcomes of a random experiment is called exhaustive cases for the experiment. Example, in a toss of a single coin, there are two exhaustive cases, head and tail. If two coins are tossed, the exhaustive cases are 2 square equals to 4. That is, head, 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 tail, 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 head. Therefore, for n coins, it is 2 to the power n. Exhaustive cases for a toss of a single die equals to 6. Exhaustive cases for a toss of 2 dice equals to 6 square. Exhaustive cases for a toss of 3 dice equals to 6 to the power 3, which equals 216. 3. In drawing 2 cards from a pack of cards, the exhaustive number of cases is 52C2. Equally likely cases. The outcomes of a random experiment is said to be equally likely if, after taking into consideration all relevant evidence, none of them can be expected in preference to another. For example, if a coin is unbiased, the two outcomes, head and tail, are equally likely. Drawing of 2 cards from a pack of 52 cards, the outcomes are equally likely. Mutually exclusive cases. Events are said to be mutually exclusive when 2 or more of them cannot occur simultaneously. For example, in tossing of a coin, events head or tail are mutually exclusive. Classical approach. The classical approach to the probability is the oldest and simplest. It originated in 18th century in the problems pertaining to games of chance such as throwing of coins, dice, or deck of cards, etc. To illustrate the classical approach of assigning probabilities, let us consider the experiment of flipping a coin. An event whose probability is sought consists of one or more possible outcomes of the given activity. On any line flip, we will observe one of the 2 experimental outcomes, head or tail. A reasonable assumption is that the 2 possible outcomes are equally likely. Therefore, as one of the 2 equally likely outcomes is a head, we logically should conclude that the probability of observing a head is half. Similarly, that the probability of observing a tail is half. When the assumption of equally likely outcomes is used as a basis for assigning probabilities, the approach is referred to as a classical approach. If an experiment has n possible outcomes, the classical method would assign a probability of 1 by n to each of the experimental outcomes. As another illustration of the classical approach, consider the experiment of rolling a die. When a die is rolled once, any one of the 6 possible outcomes 1, 2, 3, 4, 5 and 6 can occur. We can describe a sample space and sample points for this experiment with the notation S is equal to 1, 2, 3, 4, 5, 6. A die is designed so that the 6 experimental outcomes are equally likely and hence each outcome is assigned a probability of 1 by 6. Thus, if P of 1 denotes the probability that one dot appears on the upward face of the die, and then P of 1 equals to 1 by 6. Similarly, P of 2 equals to 1 by 6 and so on, P of 6 equals 1 by 6. Note that the probability assignment satisfies the 2 basic requirements of assigning probabilities. In fact, requirements 1 and 2 are automatically satisfied when the classical approach is used because each of the n sample points is assigned a probability of 1 by n. The definition of probability given by a French mathematician, Laplace, and generally adopted by disciples of the classical approach runs as follows. Probability is a ratio of number of favorable cases to the total number of cases. If the probability of occurrence of A is denoted by P of A, then by this definition we have probability of A equals number of favorable cases by total number of cases. For calculating probability, we have to find out 2 things: number of favorable cases and exhaustive number of cases. Symbolically, if an event A can happen in m ways out of a total of n equally likely and mutually exclusive ways, then the probability of the occurrence of the event is denoted by P is equal to probability of A equals to m by n. And the probability of the non-occurrence of the event is given by Q equals to P of A complement equal to n minus m by n equals to m dash by n equals to 1 minus m by n equals to 1 minus P of A equals to 1 minus P. Since the sum of the successful and unsuccessful outcomes is equal to the total number of events, we have m plus m dash is equal to n. Dividing by n, m by n plus m dash by n equals to 1, so that P plus Q equals to 1. Probability, therefore, may be written as a ratio. The numerator of the fraction corresponding to this ratio represents the number of successful or unsuccessful outcomes, while the denominator represents the total number of possible outcomes. Classical probability is often called a priori probability because if we keep using orderly examples of unbiased dice, fair coin, etc., we can state the answer in advance a priori without rolling a dice, tossing a coin, etc. From a bag containing 10 black and 20 white balls, a ball is drawn at random. What is the probability that it is white? Total number of balls in the bag equals to 30. Number of white balls equals to 20. probability of getting a white ball, or P equals to P of A equals to number of favorable cases divided by total number of equally likely cases equals to 20 by 30. Probability of not getting a white ball, or Q, equals to 10 by 30. Thus, P plus Q equals to 2 by 3 plus 1 by 3 equals to 1. A classical approach was developed originally to analyze the gambling probabilities, where the assumption of equally likely outcomes often is reasonable. In many business problems, however, this assumption is not valid. Limitations of classical approach. The classical definition of probability given above suffers from certain limitations. The definition cannot be applied whenever it is not possible to make a simple enumeration of equally likely and mutually exclusive cases. For example, how does it apply to probability of rain? We might think that there is two possibilities, rain or no rain, but at any given time it will not usually be agreed that they are equally likely. The phrase equally likely appearing in the classical definition is synonymous with equally probable. How do we know whether the probability is equal before we can measure them? If a person jumps from the top of Qutub Minar, the probability of his survival will not be 50%, since survival and death, the two mutually exclusive outcomes, are not equally likely. The definition has only limited applications in coin tossing, die throwing, and similar games of chance. The classical approach also fails to answer the questions like, what is the probability that a male will die before the age of 60? Or, a bulb will burn less than 2000 hours, etc. The definition fails when the number of possible outcomes is infinitely large. Real-life situations, unlikely and disorderly as they often are, make it difficult and at times impossible to apply classical probability concept. Relative frequency approach. In the 1800s, British statisticians interested in theoretical foundations for calculating risk of losses in life insurance and commercial insurance began defining probabilities from a statistical data collected on births and deaths. Today, this approach is called relative frequency of occurrence. The classical approach is difficult or impossible to apply as soon as we deviate from the fields of coins, dice, cards, and other simple games of chance. Secondly, the classical approach may not explain actual results in certain cases. For example, if a coin is tossed 10 times, we may get 6 heads and 4 tails. The probability of head is thus 0.6 and that of tail is 0.4. However, if the experiment is carried out a larger number of times, we should expect approximately equal number of heads and tails. As n increases, that is, approaches to infinity, we find that the probability of getting a head or tail approaches 0.5. The probability of an event can thus be defined as a relative frequency with which it occurs in n, that is, infinitely large number of trials. Consider a firm that is preparing to market a new product. In order to estimate the probability that a customer will purchase the product, a test market evaluation has been set up wherein salespeople call on potential customers. Each sales call conducted has two possible outcomes. The customer purchases the product or the customer does not purchase the product. With no reason to assume that the two experimental outcomes are equally likely, the classical method of assigning probabilities is inappropriate. Suppose that in the test market evaluation of the product, 400 potential customers were contacted, 100 purchased the product, but 300 did not. In fact, we have repeated the experiment of contacting the customers 400 times and found that the product was purchased 100 times. Thus, we might decide to use the relative frequency of number of customers that purchase the product as an estimate of the probability of a customer making a purchase. We could assign a probability of 100 by 400 equal to 0.25 to the experimental outcome of purchasing the product. This approach to assigning probabilities is referred to as the relative frequency method. If an event occurs m times out of n, its relative frequency is m by n, that is, the value which is approached by m by n when n becomes infinity is called the limit of the relative frequency. Symbolically, P of A equals limit of n tends to infinity m by n. Theoretically, we can never obtain the probability of an event as given by the above limit. However, in practice, we can try to have a close estimate of P of A based on large number of observations, that is n. In the relative frequency definition, the fact that the probability is the value which is approached by m by n when n becomes infinity emphasizes a very important point. That is, probability involves the long-term concept. This means that if we toss a coin 10 times, we may not get exactly 5 heads and 5 tails. However, if an experiment is carried out larger and larger number of times, say a coin is thrown 10,000 times, we can expect the outcome of heads and tails to be very close to 50%. Comparison of the two definitions. The two approaches, classical and relative frequency, or empirical, though seemingly same, differ widely. In the former, P of A and m by n were practically equal when n was large, whereas in the latter, we say that P of A is the limit m by n as n tends to infinity. In the second approach, thus, the probability itself is the limit of the relative frequency as the number of observations increases indefinitely. The probability obtained by following a relative frequency definition is called a posterior or empirical probability as distinguished from a priori probability obtained by the classical approach. Priori and posterior probability. A clear distinction between a priori and empirical probability is quite important for the proper understanding of the concept of probability. Priori probability is normally encountered in problems dealing with games of chance For example, dice and cards. Normally, we think of a priori probability as being deductive in nature, that is, from cause to effect, and based on theory instead of evidence of experience and experimentation. Probability derived from the past experience is called an empirical probability and is used in many practical problems. The classic example being the preparation of insurance mortality tables, which obviously are based on past experience. In the analysis of most of the practical business problems, these two kinds of probability concepts are widely used. A priori probability may be determined rather easily whenever complete enumeration is available on the various ways an event may occur. For example, the probability of drawing a king from a deck of 52 cards is 4 by 52 or 1 by 13. Similarly, the probability of getting 3 in a single throw of a dice is 1 by 6. Limitations of relative frequency approach. The relative frequency approach, though useful in practice, has difficulties from the mathematical point of view. 1. An actual limiting number may not really exist. Quite often, people use this approach without evaluating a sufficient number of outcomes. For example, Mr. Kohli pointed out that his father and mother, aged 75 and 70, both had a serious heart problem in Jan-Feb 1999, and hence, in winter, people above 70 have high probability of heart attack. His friends took it seriously and started to give special attention to their parents. 2. On deep thinking, we may find that there is not enough evidence of establishing a relative frequency of occurrence of probability. It may be observed that the empirical probability can never be obtained and one can only attempt at a close estimate of P of A by taking n sufficiently large. For this reason, modern probability theory has been developed axiomatically, in which probability is an undefined concept, much the same as a point and line are undefined in geometry. Here's a summary of our learning in this session. Discussed about the basic notion of probability. Definitions of probability. Classical and relative frequency approach, their limitations and comparison between the two.